Hello, Devox. I'm on the big screen. Hope you had a good lunch. Very amazing sandwiches. We're gonna talk about something that is probably not exciting as all the news we heard about Java, but we're gonna talk about eBPF. The name is terrible. I'll get into that in a minute. So you will hear me complain a lot about the name here, and it will intimidate myself a couple of times, but that's fine. The boring part, introduction. I'm Mohammed. I work for a audio streaming company called Spotify, and I'm also a Google developer expert for Google Cloud. Before diving into the presentation, quick show of hands. Who is using eBPF, either in his company? Okay, one. Okay, let's say three people. Awesome. Then you're probably in the right room. And why I did this presentation actually? Because I was in the same situation. So while commute is boring. I generally listen to audiobooks or podcasts, shameless promotion. Both are available in Spotify. So listening to one of those podcasts, and then it was about eBPF. And the host triggered an interesting remark. And he said that eBPF is one of those things that everyone is talking about, especially in the cloud native community and the CNCF community, but nobody actually understands. And this presentation is basically highlights my journey, and this comment triggered my curiosity. So this presentation is basically the fruit of this simple remark. So I onboarded into your journey trying to understand what eBPF is. And eBPF, its predecessor is it's a new version of BPF. Oh, that's what they aim to do in the beginning. And BPF is simply Linux socket filtering. It was a networking thing enabled to filter socket. And the language looked similar to assembly. And it basically read the packet headers. For example, here it's saying if the packet is Ethernet header based on ARP, execute the unstructured drop, go to unstructured drop, drop basically returns 0, which is false, that's the packet will be rejected. Otherwise, continue, it return -1, which is different to 0, so it's true. Then the paper was written in Berkeley laboratory. That's where the name came from. It was introduced in the Linux kernel in '97. Second BPF was the kind of the real implementation and introduced it in kernel 3.5. And then we ended up with eBPF. Now, you will hear a lot of people within the kernel community use eBPF and BPF interchangeably. That's because eBPF evolved a lot than what BPF was introduced for. So even in this presentation, I'm going to use them interchangeably, but eBPF has no relationship with BPF, the old one that was introduced in '97. So you just lost 2 minutes of your life, but that's fine. It was worth the intro. eBPF, again, is what a bad name. It's hard for pronunciation, especially if you are a speaker and you have 15 minutes ahead of you of saying the same name repeatedly. But they needed a marketing guy that wasn't available back then, and we ended up with saying with eBPF. So a little bit of context, a little bit of understanding. eBPF is a kernel technology. And when we talk about the kernel, we as developers, because I'm backend engineers, I don't develop a lot of kernel modules, neither do a lot of kernel development. But still, when we use languages such as Java, Go, you name it, we have high-level abstraction. We don't worry about memory access, file access, network access, right? We just use whatever API the language is providing. However, everything that goes needs to interact with the hardware. And that's what the kernel is, basically. It provides a system interface or system call interface. It has some API. The language that we use basically take care of that, and the kernel take those calls and transfer them to the hardware. So the kernel is basically doing the heavy lifting. And it's actually quite powerful. If we execute any command, such as ls, for example, strace is system trace, powerful tool in Linux. if you think about ls, it's quite verbose, so let's probably make it less verbose. It does all of those things. Let me make it bigger a little bit if I succeed. So it does a lot of things. You can see that 12 open add something because Linux is a file-based system, so there's a lot of file interaction. But just for ls, we don't think about it when we're executing it in Linux machines, but it does a lot of stuff behind the scenes. So Linux, the kernel is hiding a lot of functionalities. Okay, back to here. And when we want to interact with the kernel or add new functionality, we had basically two ways. Either trying to convince the whole Linux community about what we are doing. That would take probably a lot of energy, a lot of time. But let's say you managed to convince the Linux community, including Linus Torvald, and let's say it was accepted. Doing whatever needed from development and engineering work, given the fact that only 30% of whatever new features is proposed to be included in the Linux kernel got accepted. So let's say you are part of the lucky 30%. You managed to get your changes in the kernel. Yay, party. Let's start using my functionality. Well, not really. Because like the Linux distribution that we use are using Linux kernel version that are a couple of years back. And that's because, as we saw, Linux kernel is a pretty critical, pretty fundamental piece that we want to battle test it, battle tweak it in order to make the distribution as safe as possible. So aside from the engineering effort with the Linux kernel community, you would need other effort to, or a bit of time, a couple of years to wait in order to get your changes in some Linux distribution. The other option is basically to develop your own kernel module. And good luck with that, because you will be using specific kernel APIs that are not meant for outside worlds. They are not stable. That means that with each new version of the Linux kernel, you would need to update your module, and good luck. The alternative, what the Linux community realized a couple of years back, or probably more, 2012, that we would need some way to make the Linux kernel programmable. And that's basically what eBPF is a way to make the Linux kernel programmable. It is an event-based system, so everything that is happening within the kernel, it is sent an event to eBPF. We will get into that in a minute, but that's basically what it is. If there is one thing that you can keep at the end of this presentation, I remember, is eBPF is making the kernel programmable for us as developers. It has a couple of exciting features. This is one of the first emails that we're discussing in the Linux community talking about eBPF. It is user-defined, meaning that we can basically write programs that interact with the kernel. That wasn't available before. It is sandboxed, great win from a security point of view, and is executed in the kernel, which is, yeah, what we want to do. And I was hesitant to put this into the presentation, especially that I am at Devoxx, which is mainly a Java conference. There were a lot of jokes about JavaScript, but still, the Linux kernel community have this saying that what eBPF is to the kernel, what JavaScript is to the browser. Remember how the internet looked like back in the 90s, how ugly it was because we had static pages? JavaScript, as ugly as it is as a language, but it enabled us to make the browser dynamic. So we have those nice interfaces that we can make our application, front-end application dynamic. eBPF basically aimed to do the same thing. So we are now, as JavaScript was in the 90s, so there are a lot of things that are exciting coming in the eBPF world. And so I mentioned that it's user-defined, it is sandbox, and it's also executed as a native execution speed, since it's executed within the kernel, so we can benefit from almost the same speed as it was actually part of the kernel, which is pretty fantastic. So how it actually all done? We have what we call the eBPF runtime. And eBPF has two parts. There is the user space code, which is your application that will interact and collect some data. We will get into that in a minute. But we are here more interested into the kernel code. And for that, you have two options. Either you would use C or Rust. Those are the only supported languages to load eBPF programs, or kernel eBPF programs. So you write your source code, and then you compile it into a bytecode. And then you will try to load it into the kernel. So the first part, or the development part, is the user-defined part. You finish it, you compile your code, and then you will try to load it into the kernel, because that's the whole purpose. Then we have something called the verifier. And the verifier, it is what ensures what we call the sandboxing. So the verifier will make that your code is actually safe to run within the kernel. You are not trying to leak any memory. Your code will not try to crash the kernel, because remember, we're still running code into the kernel. So the verifier does a lot of job in order to ensure the safety of your code. Let's say the verifier accepted, approved basically your code. It will then get JIT compiled, similar to what we have in the JVM space. So it takes the bytecode, it compiled, JIT compiled it into native code. So what there is that's why we have kind of a native speed execution. And then it will get attached to hook points. Let's see it actually in action. So I have a very simple hello application. That's my second intimidation after the JavaScript joke. It's just I'm using Python. And that's because BCC, the library I'm using, it's quite simple to start with. So if you want to have a hello world or start with eBPF, just give it a try. BCC is a first starting point. But nevertheless, so I'm having a program here which both combines kernel code and then user space code. Is it, by the way, is the code big enough? Should I increase it a bit? Maybe I can. And then I define my C program, which you probably figured it out, is the thing that's going to be executed in the kernel. And it's basically print hello devox, nothing fancy here. So I am defining BPF as a function that's in Python provided by BCC, making my life a lot more easier. Defining the program, and then I'm defining where I want to attach the program. So again, eBPF is event-based, so where you want to listen to the events that are coming. I want to attach my program to execv. Basically, whenever a program gets executed within the kernel, I want to listen to that event. And then I'm attaching it. So I'm attaching the system call to my function. And then I'm printing for debuggability purposes. Oh, wow. That was a hard word. Anyway, I'm using a virtual machine with lemma. And then if I execute my code, and then I just forgot how to type Python 3, and it's called hello, nothing happens. Because I didn't execute anything else. If I actually go to another terminal and type something, PS, blah, 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 you can see that's actually printing my message together with some context information, like the PID. I printed PS, PS was 21 something, and you can see it here. So it has context as well. So it gives you information about the execution that's happened within the kernel, which is pretty good. So if we try to execute it with strace, my eBPF, I believe, just to filter BPF events. BPF. Yeah, you can see that a lot of things happened behind the scenes. So my program got JIT compiled at some point, and then you can see prog load here. My program is actually loaded to the kernel, and it has the unstructured count of 20. The license is GPL. So a lot of things happened behind the scenes that I didn't notice at all. OK, thank you. So that's the eBPF runtime. Again, what it ensures, since the code is actually verified by the verifier, it ensures the sandboxed environment, so there is safety and security out of the box. Now, still, there is some issues, but still, it's way better than kernel modules because it ensures that your code won't crash the kernel, which is pretty critical in production systems. It is efficient. The JIT compilation makes the code run at native speed. It ensures continuous delivery. And I executed the program a couple of times, and whenever I execute it, a new version gets deployed. So we have continuous deployment in the kernel, which is something we couldn't dream of a couple of years back, which is pretty dope. And then it's standard. A lot of APIs that we are using within the eBPF world are stable, supported by the Linux community, and everything that is there, it's meant to be supported for years to come. We come from the Java world. We understand the importance of standardization, and it's again, a big difference to the kernel module where everything is private. So you are sure that when you write your program, it's going to be supported for years to come. eBPF hooks. I mentioned that eBPF is event-based, and eBPF basically, or when you load the program, as you saw, it tries to attach it to some event. And there are more than 40 events that we can attach our program to. If I go here, you would see that there are more than 30 program types. That's a header from the Linux kernel. And there are attachment points. There are many that you can attach your program to, basically. And you can listen or attach your program to any event within the Linux kernel. And that's piggybacking on the kernel powerfulness, if that's a word. Since everything that we do goes through the kernel, being able to listen to the kernel events is quite powerful. You can listen to system calls. Whatever goes through the system calls, CPU, memory, network packets, you name it. You can listen to user space, attaching to user space. It can, without writing specific code to monitor the application, it can basically monitor calls and things within your user space application. It can listen to function, either if entry or if exit. It can debug parameters that can go into a function or hook into when a function is already executed to get output, which is pretty dope. Network. You can network to multiple layers within the network. You can even offload the programs in the network space to, depending if the hardware is supported actually, but you can offload to the hardware. So you can execute eBPF program on the hardware before even it reaches the kernel and the CPU in some specific network hardware. A lot of companies use it. It does a lot of optimizations. And yeah, I said it a couple of times before, you can basically listen to anything. Maps. To write any meaningful program, you would need some storage. And maps are actually storage for eBPF programs. They are as simple as key value stores. That's it, basically. The beneath or the underneath implementation is a key value store, but it's quite powerful. Meaning there are multiple types. There are hash tables, arrays, pretty basic. Those were the first ones to get introduced. Then we introduced ring buffers for memory optimization, LPM trees, longest prefix match, basically for resource optimization, least recently used, queue and stacks, similar to what we have in pretty much all the languages that we are using. But what's powerful, it's both the user space programs and the kernel space program can write to maps, which make it really useful. So you can basically use eBPF maps to keep the state of your program. So whenever you deploy a new version, you have a state. You can share information with the user space. For monitoring purposes, you can get information from your eBPF program, put it in maps, and then have a dedicated application written whatever language you like, extract the information, do some analysis with it, and then expose it in nice dashboards. Or you can take or update eBPF maps with the user space program. So the user space can input information or send information to your eBPF program from the maps. So there are two kind of ways of writing, which offers a lot of flexibility if you think about it. And we will get to see some things in action. I have actually a quick demo with eBPF maps. Let me create this one. So my program is exactly the same as the old one, still using C and Python. But as you can see here, I defined the hash map. I named it as syscall, and then I defined the counter and the key 59, which is the key of the execv, as I mentioned before, and the pointer. Then I am reading, I'm getting the key from my hash map if it exists. If it doesn't, if it exists, basically I update it with the value, I assign the value to the counter. If not, the counter is already initialized, and I increment the value, and then update my hash map. And then in my user space program, this block is exactly the same as the previous one, but this one is interesting. It's basically I'm looping forever. It's user space program, it's fine. Looping forever is not allowed in eBPF programs. You don't want to block the kernel. So the verifier will basically reject your code. That's why a lot of people say it's not Turing complete, because of the limitation that the verifier imposed to eBPF kernel programs. But still, from my user space program, I'm reading the values, the key, and I'm printing the key and the value of my program. So let's actually run it. Python 3, hello, is it map? Yes. Nothing happens. Again, let me try and run some ls, ps, ls, blah, blah, blah. You can see that first it printed no entry, and then you can see as I'm typing commands, it increases the value. Now, to see the job of the verifier, what happens if I remove this piece of code? This actually, the compiler won't complain. Any programming language won't complain. But the verifier in eBPF will. I hope so. Yeah, it does. And it says that failed to load eBPF program. A nice message can, or no, or value null from the map can happen because I differentiate. I'm trying to read in the P, a pointer, without actually checking it. So that's one of the things that the verifier does. It's checking that whenever you read from the value, it's actually safe to read it. Okay, moving on. Helpers. When you interact with the kernel, we don't want to write a lot of kernel programs. eBPF programs don't know how to read a value from a map. Get the time from the system, read packet network, or intercept them. So in the kernel, there are a lot of helpers defined for us that enable us to take advantage and interaction with the kernel, because that's the whole idea. So kernel expose some helpers or utility function, kind of, if you can think of, you think it that way, to make our life a little easier while interacting with building kernel programs. eBPF functions, previously that it wasn't supported to have functions within your eBPF program. What a lot of programmers, a lot of us ended up doing is tagging each version with inline to basically tell the compiler to combine our code and send it to the eBPF program. That was ugly, but that was removed now, always inline. That was removed now, and there are support for eBPF function in the kernel, and that's basically to make the kernel more modular and more composable. Tail calls. And it's an interesting way to think about chaining calls. Since there is a limitation, and I forgot to mention that, there is a limitation within your eBPF program, it can't have more than 1 million instruction. And that's a limitation within the kernel. It's a lot, but if you write any serious program, you would probably need more than that. Previously, it was 4,000, and a lot of developers complained, so they increased it to 1 million. But still, so tail calls are basically chain calls, so you invoke other programs, similar to what we do in any programming language, but the execution chain doesn't come back. So you just moving forward. So your program is actually kind of a chain. It's like calling another endpoint, but not expecting anything back. The execution will only continue forward. And that's basically to make the eBPF program more composable, and the combination of those tail calls will assemble your final code. Use cases for eBPF. It's a kernel functionality. Kernel has visibility across everything. Network is one of the big use cases of eBPF. You can use it for packet drops, firewalls, doing DDoS protection, like fixing some vulnerabilities in the Linux kernel, such as packet of death, if you are aware of it. So a lot of things that you can do. Load balancing, it's one of the great features that is available, or you can do with eBPF programs. Tracing and profiling. There are a lot of tools, a lot of even command line tools that are built using eBPF that enable introspection and add introspection capabilities to both the system and the application. Again, the kernel can see everything, so being able to debug your system with little overhead is great. Observability. There are a lot of tools that are starting to pop up that are based on eBPF with little overhead, since again benefiting from the Linux or the kernel usefulness. And they are different than user space monitoring program in a way that they are unintrusive. So we are not blocking the thread or trying to listen to any events. The kernel has visibility, events-based. It's a functionality that is built within the kernel. So eBPF-based monitoring tools are unintrusive. They are secure because, again, that's built in within the eBPF, and they are centralized. Especially in the cloud-native world, where you have multiple containers. All containers needs one kernel or talk with one kernel, so we are saving a lot compared to other monitoring tools. We will get into that in a minute. Security control. Again, all the calls pass through the kernel. The kernel can decide what packet to drop, what packet to forward, what packet to keep, what process to kill, and so on and so forth, which is really awesome. So let's assume I convinced you that eBPF is nice, and you want to start with it. There are a couple of tools. If you have no life, want to use C++, the eBPF is one of the tools that you can use. BCC, the one that I used for the first demo, is Python-based. It's really easy to use, really powerful. So if you just want to give it a start, I recommend BCC. If you are a Go developer or interested in Go or had experience with Go, you have a couple of options. eBPF Go is one of them, and also eBPF Go. And then if you are Rust passionate or Rust developer, there are a couple of options as well, such as eBPF, Rust, and Aya. And I'm going to show a demo for Aya. It works on my machine. Still happens even with kernel technologies. And that's because the whole compilation process happens within one machine, right? You compile everything. The linking happens. The linking happens in the system, and that machine has specific Linux kernel version. If you are having 100 or even thousands of servers, you can't guarantee that your version or your machines will have the same kernel. So some functionality that is available in compile time will not be available at runtime. BCC, what it does, it's basically send everything to the target machine and do the compilation and everything. Now it's using Python to do the compilation and C beneath it It takes a lot of time, especially if you have a big fleet. The response from the kernel community is basically core, very inspired from the WARA principle. It means compile once, run everywhere. Anywhere. The naming is, they have a problem with naming. They need to hire a marketing guy. But still, core is as simple as that. It's you compile your code once and then you run it everywhere. And the key component is something we call BTF, which is the BPF type format. They introduced this type format basically to ensure that within the Linux kernel, we can do the mapping between and check what is available, what's not. And in previous or further version that supports BPF, that supports BTF, they can actually do the mapping. So the compiler will do the heavy lifting. So they introduced BTF. They made some changes to the Linux kernel, to the compiler as well, to add that functionality. And that's basically it. It enables to solve the problem of compilation time. OK, time for demo. It's probably a more serious demo, but not as serious as you would hope. I'm using Aya. I mentioned it before, a Rust library to interact with eBPF program. Really cool library, I would say. It's basically, to start program, they have templates, and the templates are all the same. You just need to specify what program type do you want. You want to next to kernel program, UPRO program, XDP. My program is XDP, Express Data Path. It's a network kind of eBPF program. It has a standard structure. It comes with common library. I'm not using it. I don't need it. eBPF program is where my kernel code will live. And that's the interesting part. OK. So I can probably close this one. I don't need it. So I'm loading a couple of things here. Since in XDP program, I need to load the XDP macro. I have a map program, or map program. I have a map. I need to save something in there. And my program is basically a load balancer. So I have 4 containers in my VM machine. Doc IP, hopefully. Yes. So I have core containers, 2 backends, 1 XDP load balancer. That's where the machine or the container where my code basically will live, or the eBPF program will live. And then a client, which is simply an Ubuntu machine. Just to execute some curl command, right? So cheating a little bit here. If you noticed here that I have IP addresses within the Linux kernel, within the Docker, they have the 3 first parts similar, and then they only change the last part. You will see that I'm only changing the last part, the last part of the IP address in my demo, just to save some time. Not this one. Probably can close this one. Main rs, this one. OK, so that's what I'm doing. The program here just pulled straight from GitHub. It does not reflect what's in the server. Sorry for that, but you got the idea. So here I have the client last bit of IP address. This should be 14 or 13, I believe, and the best of the last bit of the IP address of the load balancer. The rest is actually defined. The backends is actually defined in an array. That's why I needed the map, an array, and I'm letting the user space program define that array. So if I go here, that's the user space program. A lot of things that comes with just when I load my program to give me some hints. But you can see I'm defining an array. So index 0 is going to be the first backend. Index 1 going to be the last bit of the IP address. And then you can define as many IPs as you need. So here I'm running my eBPF program, and this is where the fun part starts. So I'm reading the Ethernet header. If it's not an Ethernet header, abort the packet. I'm not interested of anything that is not Ethernet. If it's Ethernet, let it pass. I'm making sure that it's actually an eBPF4. I'm only interested in eBPF4 packet. If not, drop it. What else? I'm interpreting the TCP, basically to get the port. Yeah. And then I'm reading the source address, the destination address, and the checksum. It's really important. That's what I spent a lot of time writing this program. The checksum is a nightmare to get right. But still. And to forward or to load balance, I'm doing as simple as that. Taking, that's a helper. I'm taking the timestamp divided by 2. It's going to be either 0 or 1, and that's the indices that I have in my array. Getting a backend, checking if there is any backend. If not, I'm just printing no backend found. And then if the source IP address is actually, it's the request coming from the IP, or from the client IP, I switch the destination address. Making the destination address go to one of the IPs. Else, I'm just changing the destination request to be the client. So that's going forward or coming back, and then I'm changing the source destination to be the load balancer. So that's where actually the requests are actually going from. And then I'm calculating the checksum here. So this is a helper function, checksum. It's down here, basically to calculate the checksum and doing some debugging information. That's basically my program. So if I want to run it, readme, always forgot the comment. There is a nice readme. I will share the repo in the end of presentation. You can play with, I hope. So I'm inside my container, load balancer. It's up. Forgot about the warnings. Doesn't exist. My program is fine. And then so 12 is actually the IP address of my load balancer. If I run it, hopefully, yeah. So we got a response from 14. Again, 13, please. Please, yes. So it's basically load balance based on number of backends that I have. And there is no load balancer program in there. It's all within the kernel, which is pretty good. And the footprint, memory consumption, CPU that is required to do load balancing, it's since an kernel program, pretty fast, and also not beefy as much as beefy to traditional load balancers. Okay, I'm running out of time, so I'll move forward. So, cool demo. Should we eBPFy everything? Absolutely not. eBPF is a current technology, so be mindful about what you are going to need it for. And Brandon Gregg, which is one of the known faces within the kernel community and eBPF, said he worked at Netflix, and for Netflix size company, no more than 10 engineers need to be involved in developing eBPF program. The rest should basically know what the program is. Hopefully after this presentation you know, but to basically just spot the right use case and handle it to other eBPF programs. So not everyone needs to write eBPF programs because they are a nightmare. Where you shouldn't write when you shouldn't write an eBPF program? Whenever there is a CPU intensive kind of thing. When you need a lot of CPU, that's a user space program. Don't involve the kernel in there. You're gonna slow your whole server. It should not go there, basically. Things like application layer policy, building a control player for your service mesh, CPU intensive, you got it. So anything that requires a lot of CPU should stay away within the kernel. However, when you have the right use case, and Cilium has a nice blog from one of their clients where they noticed a drop in memory consumption, which you switch it to XDP, similar to the demo I did, but more enterprise ready. So the diagram is actually switched. I don't know why they did it that way, but I'm just taking the picture and referencing them. But they started with the good use case, and they ended up with the bad use case. Normally, it's the opposite. But yeah, it is what it is. So you can see that is almost 15 times better using eBPF program to do load balancing than using traditional user space program for load balancer, which is good. So if you have the right use case, eBPF program can be a great win. tooling. So you won't need to code eBPF programs. eBPF community have a lot of tools based on eBPF. Now that you understand, hopefully, the concepts and how it helped to save a lot of footprints from like user space, since the program actually executed in the kernel space. If you want to do something like a quick command line tool to understand how your machine is behaving, how your program is behaving, Brendan Gregg and started a program, and now it's within the BPF, called the BPF tracing tool, within the BCC IO visor. And he wrote basically command lines for every single thing that you would need to have visibility of your kernel. But they are command line based, but it's powerful. User space, kernel space, network, memory, CPU. If you want to start, you don't want to hustle. You want to use the useful utilities in the Linux kernel and eBPF. BPF tracing tool would be a good starting point. Katran, it's a load balancer from Facebook. Now it's Meta. That was open sourced a couple of years back, I think in 2018, and that's what helped eBPF to gain a lot of traction. When they open sourced it, a lot of people started, oh, you can do actually real things with eBPF. So Katran is a load balancer in in front of all Meta application, namely Facebook, that I'm sure of, but not sure about the other applications. And then all the traffic that is going through Facebook to Meta, oh my God. Anyway, Facebook, the application, it's actually going through Katran. And it's really powerful. It's using XDP, and that moment, a lot of eBPF program gained a lot of momentum. It's open source. Give it a shot if you want to use it. It's open source. Not sure what the licensing is. Cilium, another active company within the eBPF community. They have Cilium, their first product. It's basically a cloud-native solution that provides security, visibility. They even now provide service mesh capabilities. They have other things for security as well, but it's really powerful, and it's all based on eBPF. For security, again, you are within the kernel. You have full visibility. There are a number of tools available there that basically provide security out of the box for your programs or your machines, such as Falco, Tetragon, and Calico. Observability. Pixie is an interesting one. So what they did is basically they write eBPF programs. It's basically cloud native within your Kubernetes stack. They write eBPF programs that that read the events, monitoring information, save it, and then take it and ship it to their backend. So we have little overhead. The overhead that they have is 2%. When there is the maximum load, their overhead is only 2%, which is really acceptable compared to other user space tools. And all the analysis, all the backend stuff, all the heavy stuff happens on their cluster. They are now part of, I forgot the name. It's a monitoring solution company. I forgot the name. Sorry for that. So Pixie is one. Periscope is another one. It's part of Grafana, I believe. Basically the same thing. They focused on cloud-native tools, but mainly Kubernetes, but you also support on-premise, I believe. And then Parka is also getting quite some momentum. Okay, cloud-native environments. I mentioned it before. Probably I can talk a little bit more about it. If you are using containers, who is using containers in some forms? All the room. Not surprising, but containers provide isolation in the user space level, right? But within the kernel level, all the containers and pods and you name it that execute within one machine are sharing the same kernel. That shouldn't come as a surprise. And then they all share the same limit. I mean, the kernel handles the access file, the access to the hardware, CPU, memory, network, and so on and so forth. So adding functionality to Linux kernel will basically mean adding functionality to all your nodes or your containers or pods. And you can hook eBPF programs to anything and benefit from a centralized view and a centralized control proposed by the kernel, since everything will go eventually to the kernel. And this is what Cilium basically does. So if you have containers based on IP tables, networking stack, or the idea is the same, but it can change depending on how you route the traffic. But the request came in, it needs to go through all the mayhem of the network stack, and then the IP tables at the end say, oh, it needs to go through the virtual Ethernet for the virtual interface, and then it's sent it to the network, to your container, and then your container does the same. It will basically go through all the mayhem path. So you're basically your packet is doing the round trip kind of twice. Again, there are some. This idea is the same, but it might change depending on how you handle it. What Cilium does is, again, having a hash table, hash table, and or a map, and then basically when the request came in the network interface, they read it, and then you should go to that pod, you should go to that network, and to shed a virtual interface, which make networking a lot more efficient and save a lot of memory. You won't notice much difference. We're talking here about milliseconds type of performance, but still, for some type of application is really useful. And some graphs based on the same idea. And eBPF-based solution achieve as node-based as much efficiency and performance as node-based application, which means like you're calling a node to node. No virtual interface involved. eBPF-based solution performed almost the same performance, which is a great win from a latency perspective. Service mesh. Who is using service mesh or sidecar? Okay, you're going to have fun. So connectivity, a little bit of history. We started with the client libraries. We moved it to the sidecar. And I'll talk about the kernel type of connectivity. When you have a sidecar, you would need to inject it, right? So either you do it or define a namespace and some other program happen behind the scenes and inject it. If you forgot about it, then you're in trouble. The desired functionality is not there. You probably won't have any traffic, and you won't know until an email is going to your boss saying, oh, you are probably asleep. Also, from a network perspective, when the package came in, it needs to go all the way up to the sidecar, and then the sidecar, it needs to be forwarded to that node within the pod, and then it's a mayhem from a connectivity point of view. With eBPF, again, delegated to the kernel. Little footprint, little performance overhead, and that's it. You don't need to configure anything with your manifest files. You just need to inject that eBPF programs, and a lot more performant compared to the sidecar model. So there is a lot of momentum going within connectivity and sidecar based on eBPF solutions. Well, this is funny. eBPF is not only for Linux. Windows is trying to bring it to Windows Server as well, which is kind of interesting. But it's kind of those kind of information. It's just a FYI. You'll probably just forget it the moment you walk away. But it's worth giving a a shot. eBPF Foundation, a lot of major companies are there. They're basically using eBPF, and they want to, similar to the GCP that we have in Java, it's basically steering where we should invest next in eBPF and what's best for the whole community. A lot of companies are there, which is pretty good and healthy from a community perspective. Into the future, eBPF, I mentioned it in the beginning, it's kind of enable a program, making the kernel programmable. So we are kind of moving away from putting in everything in the kernel. The kernel is, up until now, was a monolith application. We're going to probably start getting away some functionalities within the kernel and making everything eBPF. Hotfixes could be done pretty quickly with eBPF, and so a patch using eBPF could be released pretty quickly, and until there is a proper fix within the kernel, especially Linux or kernel zero-day vulnerabilities. I'm right on time. Perfect. And there are a couple of links that helped me. So the demo is there, and great book from Liz Rice, and also from David and Lorenzo. Both two books if you want to read more about eBPF. And with that, I want to thank you. I probably don't have time for questions, but I'll be around and I'll be here for the 10 minutes until the next speaker comes in. Thank you very much.